Autonomous drones are an example of a quickly advancing technology that might become very familiar to us in the near future. Drones today are able to fly unmanned at standard speed, avoiding obstacles thanks to computer vision. However, their speed is limited by the latency in the control flow between sensors, processors, and motors. An image detected by a camera takes a few milliseconds to be transformed into control signals for the engines, a latency that can be fatal. Decision-making is often driven by machine learning models, translating into high energy consumption from the internal processor. Should the flight conditions change, the drone is not always able to adapt. Consider instead the humble parrot. A parrot has a small brain, weighing a few grams, and burning a small amount of calories. Yet, it manages to avoid obstacles much faster than the drone. It flies faster, and it quickly learns to adapt to changing conditions, in flight or on the ground. So what makes a bird-brained parrot smarter than a drone? The parrot's brain works asynchronously. It quickly receives stimuli from select parts of the body and reacts to those stimuli by executing a number of simultaneous actions, an impossible feat for the pipeline-bound calculations of the drone. Of course, there are things that the parrot will hardly be persuaded to do, such as recording video or delivering packages. Still, wouldn't it be nice to port some of the advantages of the parrot's brain to drones? Neuromorphic engineering is a new, brain-inspired computing paradigm that promises to do just that. As a PhD student at Politecnico di Torino, the goal of my research is to analyze and catalog the hardware and software tools currently available in the neuromorphic field, to investigate their promising new applications in industry, and identify strategies for their implementation using neuromorphic technology. The building block of neuromorphic engineering is the spiky neural network, a type of artificial neural network mimicking the mechanics of real neurons and therefore characterized by sparse computation. In the last decade, a number of spiky neural network hardware accelerators have emerged, such as the University of Manchester's platform Spinnaker and Intel's own entry, the Loihi chip. Spinnaker is a fully digital board based on ARM chips. This makes the platform highly programmable, which allows to expand its SNN simulation capabilities with custom code, such as MPI libraries. Because its simulation is entirely defined by software, Spinnaker is not bound to any neural model, and we can program it to accommodate cutting-edge models, which enable faster learning. These systems have the potential to perform online learning and dynamically adapt to new situations, continually devising new strategies to make sense of unlabeled data. Thanks to sparse computation, spiky neural networks running on dedicated neuromorphic hardware are very low power. This makes spiky neural networks and neuromorphic processing a great match for IoT and edge computing. For instance, we are able to perform real-time human activity recognition on raw data recorded from low-cost sensors with similar precision to convolutional neural networks and half as many programmable parameters. Neuromorphic sensors also enable new possibilities beyond sound and vision. Braille letters read by an event-driven robotic finger can be classified by a spiky neural network within an acquisition and processing pipeline that's fully neuromorphic from start to finish. With new encoding schemes, neuronal models, learning techniques, network architectures, hardware platforms, and software environments, neuromorphic engineering is moving its first steps into the industrial world. And by bringing together all these complex tools, I am helping build a powerful and accessible toolchain that will hopefully soon bring this innovation into everyday life.